Part 2, you need to do two things. The first one, I think you should be fine. The first one, we use math formula, the Fibonacci formula, so we can estimate. But the second, based on what I, communication with a few students, I feel you didn't get it. Yeah. So, and in my description document, I didn't say much. And then in class, I talked about a little bit. Yeah, but to understand that, I need to give you more information. Okay, all right, so that's 8.1, detect overflow by special method. Yeah. Our method number 1, we use math formula. So it is the math way. Okay? The method 1, math formula. So method 2, you should not use any kind of math formula again. So the method 2, you need to use the typical CS method. The programming way. You write a program, so you keep going, calculating the Fibonacci numbers until you get overflow, you stop. Okay? Yeah. If there is no overflow, keep going. Okay? Yeah. For example, F1, F of 2, and so on. Okay? Keep going. F of 92, still fine. Remember, method 1 tells us when n equals 92, you can calculate the correct Fibonacci number. But when you get F of 93, overflow. Right? Overflow. But this method, we want to detect overflow directly without using formula. Using some appropriate CS method. Here, I'll give you that. In the, one of the previous videos, I give you a keyword, right? So I said exact. You use exact, this keyword, when you do the web search. Here, let me give you that method. All right. So here, method 2. Okay. Yeah. Method 2, another thing. For the method 2, our main concern is overflow. This is our main concern. Right? So another thing I like to remind you here, because so these two methods, this is in part 2. Part 2. Okay? All right. Then we have part 1, part 3. Part 1, iterative, we use the, not iterative, sorry, recursive. Yeah, because we want to recursive with redundancy, right? A lot of redundancy. That's the reason it's very slow. Part part 3, we do dynamic programming. Okay, so we can get, some recursive method without redundancy. The result very fast. Okay, yeah. Part 1. So I'd like you to do some experiment. The execute response time around 30 seconds. 30 seconds. Because if you have a relatively faster machine, you need fewer than a second. Okay? Typically, you do testing n around 45. Okay? 40 something. So then you can increase, decrease, to control the response time around 30. So 20 something or 40 something, all fine. Okay? Yeah. But just let you know, when you use nearly 30 seconds, you can only do Fibonacci calculation and around 40 something. That's very slow. Okay? That's very slow. But when you do part 3, dynamic programming, and use, so here in Java we use big integer, we do not have overflow. So we know we can do much larger. The Fibonacci number, I ask you to test f of 10,000. 10,000. So compare 10,000 and f45. Huge difference, right? But fractional second, right? Less than, one student showed me yesterday. So 0.00 something second. Very fast. All right. So that's, I recall, because this part related to our part 2. In our part 2, method 1, math formula. So you do not have this question, math 1. But the math 2, do not use the slow method, okay? Do not use the slow method. Yeah, because we have a better method. Why we do not use it? We use that dynamic programming, okay? Yeah. So when you use computer way to detect overflow, you need to run a method, right? Yeah. So run this method 2 here, so here, okay, so this method 2 here, apply the dynamic programming algorithm, so dynamic programming algorithm on the long integer, correct? Long integer data type. Okay. So running very fast. Okay. Sooner or later, you will hit overflow, right? So Fibonacci iteration. So here more specifically, because we know when we do dynamic programming, we define a recursive function using the dictionary method. because you create a dictionary. Okay? You create a dictionary. And every time when you need to calculate a new Fibonacci number, you look up in the dictionary first. If it is not available, you do recursion. If it's available, just retrieve it. Dictionary method, right? So this way. Right? Then, sooner or later, you need to do a calculation f of n equals f of n minus 1 plus f of n minus 2, and this step would give you that overflow. The overflow would occur, and you would need to catch it. Catch that overflow. As soon as it occurs, catch it, stop. Okay, all right. Well, how? Right? So next slide, I tell you how to catch it. Catch it with a special method. So what's that? Look at here. Here, I find some document online. Look at this method. Math.addExact. This is the method you use to catch the overflow. Okay? Math. Yeah, math class in Java. So in Java, math class. Okay? Here, we're in Java. There is a class called a math class, capital math. So a lot of math operations you can do inside this class. But we use the addExact static method. addExact. Yeah, you can do addition, but this addition must make sure your calculation is exact. No overflow, no underflow. All right? If there is overflow or underflow, you also check the underflow. Okay? Overflow out of range from the upper bound, right? So you have a range. You have a normal range. Okay? Lower bound and upper bound. When your result, get out of the outbound, upper bound, overflow, out of the lower bound, underflow. Okay? So this method would return an exception object. So you can catch that exception object. You stop. All right? Yeah. So here the exception. So look at this. The static method addExact performs a normal addition. Now, if nothing is wrong, you get a correct Fibonacci number. Okay? Yeah. So put in your dictionary, addExact. But throws an exception if the operation results in an overflow or underflow. Right? So the exception here is the arithmetic exception, whatever it is, so it's not important. Okay? So you just write a catch block, Java, in the catch block. That's the place you can handle this overflow. Okay? So you can, because that's the place you detect the first n number that causes the overflow. Based on what we have at this time, we know that should be 93. Okay? So when you hit N93, you get your first exception. So you should stop. So you do not keep going because you get it. You get it. So using this addExact. All right? Yeah. Dynamic program. So you can do it very fast. Okay? Yeah. you increase that n number, all right? So you can use a for loop or while loop, whatever, just keep going, okay? Before you get an overflow, you keep going, okay? Until you get your first overflow, then, you bring out some output message, then you stop. That's the part 2, method 2. That is what I mean. You should use the computer science way to get overflow, not the math way. Okay, 2 different ways. So we want to compare. If they return the same overflow line, right? So we need to find that line. Okay? Before that line, no overflow. After that line, there is overflow. Okay? Do not use the negative number, positive, negative. Negative number way not reliable for overflow. Okay? Yeah, because I heard some students, when I asked them to detect overflow, because in our project one, remember, I want you to feel about overflow, so I use the example using -1. Okay? Yeah. Because -1 just give you that impression. If you are not aware of the overflow problem, you will get a ridiculous answer. That's the purpose. But that's not a good detection method. Okay? Yeah. So here, let me explain why that's not good. So do not use some negative output to detect the overflow, because this method not reliable, not. All right? Yeah. Why? Let me explain a little. Why it's not reliable. Overflow, remember, when overflow occurs, the computer does truncation. Okay? Does truncation. Only keep the last few bits, last certain number of bits. Okay? Yeah. Higher than that, the bits higher than that, long integer, we know 64 bits. So higher than that, truncated, no matter what, truncated. All right? After truncation, we know the sign bit, the highest bit, we call a sign bit. Sign bit could be 0 or 1, right? 50% 0, 50% 1. And we call the highest bit sign bit. 0 corresponds to positive. And positive, let me just use the plus sign. 1 corresponds to negative. So if you use negative output to do detection, you can only catch 50% overflow. The other 50% you cannot catch. Right? So that's why I would say not reliable. Right? Not reliable. But here, if you use this add exact way, you can catch the overflow 100%. How about that? 100%. Okay? You won't miss it. Yeah. So that's the right way to do part 2, method 2. How about that? Ready? All right. Not too hard. Yeah. Not too hard. Okay? Yeah. Dynamic programming. So you already use it. All right? This time on long integer. Add exact. Okay? Yeah. Running time should be very fast. So you don't worry about that. Okay, so that's those. Any other questions about the project 2? All right. If no question, let me move to second topic. Efficiency, Quicksort, because you may need to use this knowledge in about 2 questions. 2 questions in your homework assignment number 2. Yeah, so let me jump there. Bring up Module 4, Part D. D.5. Let me talk about worst case efficiency first, because that is very easy. Very easy. Okay? After that, then best case efficiency, a little harder. Okay? Yeah. So for the worst case, the idea is pretty straightforward. Yeah? Because based on our experience, we know when the worst case occurs. We have experience on that. And here we apply divide and conquer approach. Divide and conquer, so that one array is split into 2 subarrays. When you do the split, there is a consideration if your split is balanced or not. How balanced your split is. If it is very balanced, then the efficiency is much better. If it is, very unbalanced, then the efficiency is very poor. So for the worst case, we want to do the most unbalanced split. That would correspond to the worst case. That's simple. Okay? The most unbalanced split. So what's that? Most unbalanced. Suppose this is the original array. Okay? We split it into 2 subarrays. Cut it somewhere. Okay? The most unbalanced, there is only 1 element in the smaller subarray. Only 1 element. Because you cannot do 0 and the n split, right? Because that's not a split. If you do a split, the most unbalanced split is 0 and n minus split. Okay? So if, when you do split, all the way, everywhere, you always do this kind of split, that corresponds to the worst case. Okay? Oh, so then, with that understanding, here I just use an extreme mode example to show you that result. All right, extremely unbalanced case. Here, the pivot. Here, so yellow color, see, other than the pivot element, So actually here, in our implementation, other than the pivot, all elements belong to one of the subarrays. So pivot element here we treat as that one. Although not, we modify our understanding a little bit. That is the one. Okay, all right. S region, the remaining, all right, yeah. Okay. Or another possibility, other than the pivot element, or in green color, L region, yeah, L case, yeah. These 2 cases. All right, yeah. So you keep, everywhere you keep using these 2 cases. Right? Then, at the end, you will get the worst case efficiency. Worst case efficiency. All right, yeah. here, we need to do n-1 comparisons. This kind of partition, you need n-1 comparisons. But after this partition, you only reduce the file size by 1, right? Because the n-1 subarray, you need to apply this divide and conquer another time. You also you get extremely unbalanced split. All right, yeah. So you can see that these two slightly different. Yeah. So here I ask you, because for this case, uppercase, you don't need to swap, right? The P already in place, but the lowercase, P is not in place. You still need to do one swap operation. So that means both correspond to the worst case, but the lower one is slightly worse than the upper one, because you need to do a little more work. Okay, slightly more work. That's the point I want to convey here. Okay, all right. Recurrence equation for worst case. Now we can write out the recurrence relation for the worst case. Running time complexity function. Suppose we use T of n to represent total number of comparisons. Now let's write the equation. T of n equals T of n-1 plus n-1. Because this partition, we need to use n-1 comparisons. All right, yeah. So that non-recursion cost, that's the non-recursion cost. Okay? Because the recursion, we need to keep doing the recursion on T n-1 and so on. Okay, yeah. So this recurrence relation, you just do iterations step by step. So you will get the first time you have this n-1 term, the second time you have n-2 term, and so on. The last one you have 1. You need to add 1 comparison. Okay? Yeah. Adding up all these numbers, so you get this final expression for the number of comparisons for the worst case. So you can see this is in the big data of n squared. Okay? So very bad. The quicksort, you cannot avoid very bad worst case. Quicksort, you cannot avoid it. Okay? Yeah. It could occur, but why people still use it a lot? Because the percentage for this case to be occurred very low. Why very low? You can see every time when you do split, that's this 1 and -1 split. That could be percentage very small, right? The first time it is already small. The second time, even smaller, right? But you need to accumulate. So the final overall probability for this worst case to happen, extremely small. That's the reason, people just take it to get extremely good overall efficiency. Okay? Yeah. All right. So that's the worst case. Next. All right, yeah, so here I run some example. I run some example, step by step. But here I think you can see it easily, right? You can see it easily. All right, so this example, sometimes you get an S case, sometimes you get an L case. So that could occur, all worst case, okay? All right, yeah. So, but that's enough for the worst case, okay? Now let's look at the best case efficiency. Best case, we just take the opposite scenario, opposite. So what's the opposite? Most balanced split, right? The previous one, most unbalanced. Here, most balanced. So then we try to find the efficiency formula function. All right. Most balanced partition. S region, L region, almost the same. Okay, almost the same. So our recurrence relation T of n equals 2 times T of n over 2 plus big theta of n. Big theta of n. Okay. Here, because this asymptotic notation, if you want to use it in the calculation, it's quite annoying. Right? Yeah. So remember, when this happens, usually we replace it by some constant multiple c times n. Then we can do, normal calculation. Otherwise, how can you do normal calculation? With asymptotic notation, you cannot do normal calculation. Okay? Yeah. All right. So here, let's do the calculation, but here I like to use a recursion tree way to do the calculation. Recursion tree, so it's a graphic way. So we draw diagrams, graphic way. So we can, do analysis on that binary tree, and we can estimate T of n, the total cost T of n. As an approximation, it's a good approximation. Okay, it's a good approximation. All right, so let me show you how to use the recursion tree to estimate. Here we do estimate. Okay, all right. When we draw a recursion tree, we need to know how many levels do we have in the recursion tree. Okay, how many levels? So this inequality here, we want to estimate the number of levels. Because we keep splitting. N over 2. Every time we split in the middle, N over 2. Keep splitting. Okay? Yeah. So we assume N is between 2 adjacent power of 2 numbers. 2 adjacent power of 2 numbers. We can always get that. So we can find, the bottom level, because every time when we split a tree node, we get a tree node with size, with data size. N over 2, N over 2 to the k plus 1. And if the size is less than or equal to 1, we should stop the split, right? Yeah, think about that. We should stop the split. Stop the split. Okay? All right. So here, let's do the split. All right. Non-recursion cost. Here, in this tree, we accumulate non-recursion cost. Every time when we do recursion, but this term, it is out of the recursion. As soon as it appears, it won't be carried to the next recursion. Okay? It stays there. So we accumulate this part of the cost in all levels. Top level, just the Cn. Next level, Cn over 2, well, we have 2 nodes. Right? So if you accumulate second level, you still get Cn, right? Third level, each node Cn over 4, but you have 4 nodes. So if you add them together, you still total in this level, you get Cn, and so on. So all levels, if you accumulate non-recursion cost in all levels, each level Cn. So then it's important to estimate number of levels. Okay? The level number, here we know this, because here you can see this actually corresponds to k equals 0. K equals 0. This one, k equals 1. The last one, k. Okay? So you count from 0 through k, actually it is k plus 1. Okay? You need to have k plus 1. But k plus 1 still approximately equal to log base 2 of n. Approximation. Here we use approximation for the estimate formula. So the total cost should be big theta of n times log n. For the best case. This is the best case. Okay? The best case. All right. Quick sort. But how about the average case? Because we are most interested in the average case. But for the average case, if you want to use this way to estimate the average case, rigorously, it could be very hard, right? It could be very hard. But there is some easy way to estimate average case. Yeah? Because think about it. For the best case, so for the average case, right? So for the average case here, if you really want to estimate, there is still some way, because you can think about here. When we do partition, the best case you use n over 2 comparisons, right? N comparison. N comparison, yeah. Right. Yeah. The estimate could be very complicated. So that's why people do not do average case efficiency for Quicksort. So, but how do people see that the average case for the Quicksort is very fast? By experiments. So people do comparisons, many sorting algorithm, merge sort, insertion sort, heap sort, Quicksort, all those, they apply them on same set of data, do many experiments, then do statistics and see which one is the fastest. Okay? People do it in that way, not this analytical way. Okay? Because too complicated here. So this tells you doing the rigorous analysis, you have limit. Because many times your mathematical tools cannot solve the problem. Too limited. Mathematical tools has a lot of limitation. So people do experiments. When mathematical tools are not available, do experiments. All right, so that we finish our second topic. Yeah, so now there were several questions, efficiency in the homework assignment number 2. So you have this background. We can answer the question. Okay? Especially there is one, as I remember, which sorting algorithm has the largest difference between the worst case and the average case, right? Yeah. So something like that. Okay. Yeah. So we compare worst case and average case. Which one you will get the largest difference? Something like that. Yeah. So if you look at that question, my hint here, suggestion hint here, you look at asymptotic notation. The worst case, what's the asymptotic notation? The average case, what's the asymptotic notation? Are they in the same category? Yeah, because asymptotic notation, yeah, when we consider best case, worst case, average case for sorting algorithm, basically we have these 3, right? Yeah. Best case, some of them could be in the theta of n. Okay, for example, insertion sort. Okay, yeah. Big theta of n log n. All right, yeah. And big theta of n squared. Now we need to compare the worst case and the average case. We want to see if they are in the same category. Then we feel, their difference is not too big. If these two efficiencies fall into different categories, then we treat them, the difference will be larger. Okay? Larger than the same category. Okay? Same category. So you look at from that point of view. Okay? This point of view. Otherwise, it's hard to compare. Right? Hard to compare. Same category or different categories. All right, so that's what I like to talk about. Okay? If you have any question, you can let me know. Okay. I just based on the questions some students ask me, so I explain here. Next, I want to explain another question we used before. Yeah. Remember, we find the second largest element in 4 elements, right? Only 4. 4 elements. How many? So we have several questions in our homework assignment midterm related to this question. But here I want to do the general version. Find the second largest element in an element array. Here there is an interesting method called a tournament method. So I want to introduce. So these 2 weeks, starting from today, 2 weeks before the final, these 2 weeks we use for review for final. Okay, review for final. So I will, mainly talk about some questions related to final. All right? Yeah. So here, when I talk about this one, there is a good chance you will see it in the final. Okay? let me jump back to the previous one. I have this 8.2. Find the second largest element. So here there is an interesting method called tournament. So you organize, some sports game using the tournament way, right? There are n players. You want to organize them to play, in several rounds, using the, elimination way. If one player beats another one, the losing player would be eliminated. Only winners can move to the next round, right? For this kind of rule, so we want to use that to solve the second largest element problem. All right. So the method because if we use this way to understand, a lot easier. Okay, a lot easier. But here, when you organize, competition in this way, here you should consider n usually is not power of 2. Okay? In general, n is not power of 2. If n is power of 2, then it's perfect, right? Every time you eliminate one half of the existing players, that's the easiest scenario you can have. But in general, we don't have that. Okay? Sometimes when you try to pair the players, but you have odd number of players remaining. So one player would move to the next one directly. Yeah. So you also need to consider that in that case. Okay? All right. So here, let me draw the diagram. So we try our best to pair the players. Okay? Sometimes based on their strength, right? So like chess players, for example. Okay? So because they have some points, grandmaster, that kind of points. Yeah. All right? So we can organize like that. Okay? All right. So that's the current round. If one player idle, just just lucky, no player available, move to next round directly. Okay? So next round, and so on. Okay? Pair like that, pair like that. Okay? And so on. Then there is a final round, right? Final round. Only 2 players left. So you get a final winner. Oh, sorry. Final winner. Okay. All right. Here, can we interpret this final winner, the largest element? Can we interpret, largest element in the array? Yeah. Because here, every time when we when we compare two elements, the larger one is the winner here. So the final winner is easy to identify, right? It's easy to identify. So a little harder question is, so after we identify the largest element, we have that. You can assume we have it already. Okay? After we identify the largest element, okay? How to find the second largest. Okay, think about this question. What's the relationship between the largest element and the second largest element here? Definitely, the second largest element has to be lost to the largest, right? Yeah. Has to be a loser when it is compared with the largest element. Okay? Yeah. That's obvious, right? Yeah. So, in other words, the largest element has to beat the second largest directly. How about that? So we make this observation. All right. So property 1. The largest I just write largest, okay? The largest has to beat the second largest. Directly. How about that? Okay. Think about that. All right. Probably 2. The second largest beats all other players, all others except the largest. The largest. Okay? All right. Except the largest. Yeah. The second probably pretty straightforward, yeah, but it's useful. Okay? All right. So here we focus on largest and second largest. These two players, very special. Right? Right. And here we need to find the candidates for second largest. Candidates. how to find the candidates for second largest. Okay, candidates. Because many players, they are not qualified to be the candidates for the second largest, right? Many players, they are not qualified for the candidates for the second place. So we want to eliminate all those players who are not qualified for the candidates for the second largest player. Not qualified. Okay? Now, the most important observation, probably, we need to find. Probably three. Okay, probably three. To be qualified for the second largest element, to be qualified, we want to find that critical problem. So this one is the critical problem. Okay? To be the second largest. Okay? Then it must be, so here, let me state it first, then we try to understand. It must be the direct losers to the largest. Direct losers. Direct, not indirect. Direct losers to the largest. Direct losers. Okay? Because think about it. Each round, the largest beats one of the players, right? Each round. Okay? Move to the top. Yeah? Each round, the one that is beaten by the largest, that could be the candidate. Okay? Okay. Moving up. Yeah. If some players not beaten by the largest directly, that player is even not qualified for the second largest because it would be beaten by some other player, right? So that player already beaten by other players, but other players better than this one, the other players could be qualified for the second, but this one cannot be qualified for the second, right? Think about that. That's the critical observation. That's the critical observation. With this observation, then we can get the final formula. Now we are ready to get the final formula. To get second largest formula. Okay? Oh. The first step, because we need to get the largest first. To get the largest first, we need to do enough comparisons to get the largest. And we know the minimum number to get the largest, that is n minus 1. Okay? The minimum number. n minus 1. Okay. Then, so second part, we need to find the second largest. Second largest, we need to look at the candidates beaten by the largest element directly. How many rounds do we have? Okay, how many rounds do we have? We need to estimate that. Okay, all right. Because at the top level there is no rounds, right? If the last player remains at the very top, no match, no game. So we only count the number of rounds before that. Before that. Okay? All the levels before that. Okay? Yeah. So that number exclude the top level. So that number is floor function log base 2 of n. Floor function, not ceiling function, floor function. Okay? So if you're not sure, you can plug in a few numbers and then test if it's the floor function. Okay? N equals 3, 4, 5, and C. If it's okay. Okay? 3, 4, 5, floor function. How many rounds? First round. Okay? Yeah. But the number of candidates, this floor function, we need to find the largest in these candidates. So another minus 1. Okay? Another minus 1. Then simplify a little bit so we get a final formula n plus floor function of log base 2 of n minus 2. Okay? So the final formula is this. Formula for this. Okay? From now on, when I ask you to calculate this kind of calculation, you just plug in this formula to give me the answer. Okay? All right. Sorry. Yeah. All right. Yeah. Okay. So that's it.